Welcome back to our continuing discussion of quantum theory. In this lecture, we're going to talk about the rise in the 1960s of quantum chromodynamics, the theory of the strong force that holds the nucleus together. And then in the next lecture, we're going to sort of round off the history of quantum theory by talking about the rise in the 1980s and 1990s of the unification of the various underlying forces of nature, referred to as the Standard Model. But first, the rise of the strong force in the 1960s. We have been talking about quantum electrodynamics, using that as the name for the phase of quantum physics that developed in the 1930s and 40s after P.A.M. Dirac's introduction of his relativistic theory of the electron and his textbook of 1930, which triggered a kind of a new paradigm for physicists and chemists working in areas to which quantum theory could be applied. And we talked about some of those applications in the previous lecture. In 1946, physicists confronted one of the problems with quantum electrodynamics that I described earlier, which was that the theory is riddled with infinities, with tricky little mathematical infinities that need to be discarded, but in a non-arbitrary way, if at all possible. And three physicists independently came up with solutions to this problem. In 1946, the American physicists Julius Schwinger and Richard Feynman, and really independently, the Japanese physicist Shinichiro Tomonaga, who was working in the wreckage of Japan after World War II and somehow managed to maintain enough contact with what was going on in physics in the Western world that he too formulated a solution to this problem. And the solution is it's really a kind of a mathematical trick, and given the name renormalization, the approaches looked very different, but they turned out to be mathematically equivalent, which is again one of these startling developments. You recall that in 1925, Schrödinger and Heisenberg had come up with independent solutions to the crisis that early quantum theory found itself in the 1920s, when spectroscopic data no longer matched the original formulation of quantum theory, and their approaches looked totally different, and in 1926 they turned out to be mathematically equivalent. Here again, Feynman and Schwinger had come up with what looked like radically different approaches to solving the problem, and they turned out to be the same solution, and that was the case for Tomonaga as well. But notice what's happening here. In the case of Dirac's relativistic theory, which generated negative solutions to his equations, which he interpreted physically, and that led to the prediction of the existence of antimatter, and that was discovered. And it also led to this theory that the zero energy level was rich with virtual energy, and so protons could sort of pop out of that, photons could sort of pop out of that. In the case of these infinities, physicists had no qualms about not interpreting those physically. How come the equations generate all these infinities? Just a mathematical problem. Let's get rid of it. It's not relevant to us in physics. So I guess you have to have a lot of, obviously one does have to have a lot of intuition, but there's a sense in which physicists use their intuition in ways that perhaps could be considered non-logical. Maybe that's the nature of intuition, to be non-logical. And the infinity problem went away, and quantum electrodynamics from 1946 on was implemented and used far more intensively than it had been before. The interesting little anecdote, since we're talking about Schwinger and Feynman sort of repairing a problem with Dirac's theory, Dirac married Schwinger's sister. Dirac was an extraordinarily quiet man. I had only one occasion to meet him, but he was an extraordinarily quiet man for reasons that I won't go into. He had a psychologically very abusive father, and so he spoke very, very little, and he was very shy, extremely shy. He wound up marrying Schwinger's sister, and a European physicist came to visit them sometime after they got married, and he visited them at home, and Dirac let him into the house, and they sat and they chatted for quite a while. And Schwinger's sister, Dirac's wife, was sitting on the couch as well, and it was quite a while, according to the visiting physicist, perhaps an hour or so, before Dirac realized that he hadn't introduced his wife. So he just casually said to the physicist, this is Schwinger's sister, and went on. Subsequently, Dirac claimed that, well, eventually he said, and it's my wife, whom I married, but the story sounds better when you say it was Schwinger's sister. In 1953, Abraham Pius, a refugee physicist here in the United States, and Murray Gell-Mann, an American physicist at the California Institute of Technology, both independently published reviews of, spoke at a conference and gave reviews of the state of quantum theory up to 1953. And using two very different lines of reasoning, they both came to the same conclusions, in which they abstracted from the previous 30 or 40 years of quantum physics a recognition that there were, in fact, quantum theory was dealing with four fundamental forces, which I've already telegraphed in previous lectures, that the theory of there's a strong force holding the nucleus together, there's the weak force that is responsible for the stability and instability of the neutron, is related to the release of electrons when in radioactive decay, that there's the gravitational force, and there's the electromagnetic force. And that, in effect, what physicists have been doing is been treating these forces in a compartmentalized way, and the ideal would be to treat them in a unified and integrated way. Now, this becomes then, starting in the 1950s, a goal for physics. But we're not ready for that yet, because for one thing, while we have a theory of the electromagnetic force, namely quantum electrodynamics, while we have a kind of patched-together theory of the weak force through Enrico Fermi's 1934 theory of beta decay that we've already mentioned, and QED, which together kind of cover the weak force, and let's call that a theory of the weak force, and we set gravity aside because we don't need gravity at this level of physics, we don't have a theory of the strong force. And that's what has to be put in place before, in a certain sense, we can begin the process of unification. Now, as a matter of fact, as we'll see in the next lecture, that process actually overlapped the rise of quantum chromodynamics, namely the theory of the strong force. But we will talk first about the rise of the theory of the strong force, and then cover unification. In 1962, the same Murray Gell-Mann, now 9 years older, Gell-Mann and an Israeli physicist named Yuval Ne'eman proposed a solution to what had become a really irritating problem for physicists. And that was that by 1962, because of the explosive growth in the power of particle accelerators, which we've discussed before, that the number of so-called elementary particles found from smashing atoms together had now exceeded 200. There were over 200 elementary particles, and that seemed ridiculous to physicists, that you can't have over 200 elementary particles. Gell-Mann and Ne'eman proposed a rather elegant way of organizing the 200-plus elementary particles into 8 families of particles. And in fact, Gell-Mann, who has an impish sense of humor, called this the Eightfold Way, which, borrowing a term from the Buddhist theory of virtue, the Buddhist doctrine of the way to virtue, the Eightfold Way is a way of organizing all of these 200-plus particles into families. So at one level you say, so that's like the Dewey Decimal System in the library. What is the big deal there? Well, Ne'eman and Gell-Mann predicted that since there was a gap in one of their families, they predicted the existence of a particle that would complete that family line. That particle had never been observed. And they were saying something like this: if our classification scheme is valid, that particle should exist. Mendeleev had said things like that based on the periodic table, where there was a gap in the table, and said, well, there must be an element that fills this gap. And in that same year, at Brookhaven, using the cosmotron accelerator that we've described, the omega particle was described. That was a name given to the particle by Gell-Mann in advance of its discovery again, somewhat whimsically, based on the biblical phrase in which God is described as the beginning and the end. In Greek, I am the Alpha and the Omega, Alpha being the first letter of the Greek alphabet, Omega the last. And so he called that the Omega particle because it would be the last particle in that particular family. Now, this is kind of interesting for the reason that perhaps has already struck you. How can a classification system predict existence? No, if I classify books according to, let's say, the Dewey Decimal System, and maybe in the Dewey Decimal System, 891.325 would be the name of the number attached to a biography written by someone and published in a certain year. Now, that doesn't mean that that book exists. It just means that if that book existed, this would be the number that the classification system tells us that we have to assign to it. And yet here we have a classification scheme, and this came up again in the table of the periodic elements and in Bohr's 1922 quantum version of the periodic table, where there were gaps, and we say, well, there must be something to fill in that gap. Well, that suggests that this classification scheme has a connection with reality that goes beyond mere classification, as in, for example, the Dewey Decimal System. Well, over the next few years, Murray Gell-Mann, who plays the pivotal role in the rise of the strong force theory, and a scientist at CERN named George Zweig independently developed a theory of the strong force going beyond this classification scheme to a theory of the strong force in which they assumed that protons and neutrons are not elementary particles. Now, we already know from the 1930s that the neutron is at best an unstable particle because outside the nucleus it disintegrates into a proton, an electron, and a neutrino. But the proton, that sounds pretty elementary. But what happened at the Stanford Linear Accelerator, one of those linear cyclotron machines that was built by a student of Ernest O. Lawrence, David Sloan inspiring that design, and that machine, which continues to exist in upgraded form right into the early 21st century, has been the source of major developments. It's a roughly 2-mile long linear accelerator. They had been smashing electrons into protons, and the protons disintegrated. The protons came apart. That was the clue to Gell-Mann and Zweig that protons were not elementary particles, and they proposed that a radically new theory of matter. The new theory of matter goes like this, and this is the one that at the beginning of the 21st century still holds the field, that there are two families of particles. One family are called leptons, and the most famous member of that family is the electron. The electron and all other members of the lepton family, of which there are 6 members, the electron is the one that we know best, but there are 6 members to that family, 3 normal sort of particles with mass and charge, and 3 neutrinos, one that is associated with each one. So you've got 6 leptons. They only respond to the electromagnetic force and the weak force. They don't respond to the strong force at all. That has nothing to do with them. And then there are hadrons. That means every other kind of particle belongs to the family called hadrons. All hadrons are made of quarks, some combination of quarks. Doesn't matter how many hadrons they are, because we can make as many as you want out of legitimate combinations of quarks. The quarks are held together by particles called gluons. Gluons glue quarks together, and there are 8 gluons. In 1964, the mathematician Oscar Greenberg realized that gluons had to come in different styles, so to speak. They had to have some certain distinctions, and so he assigned them one of 3 different colors. And so the gluons, there are 8 of them. They come in 3 different colors, and the color is called a charge. So they have color charge, which has nothing electrical associated with it. So now we're beginning to see a picture of how matter is constructed. It's constructed out of leptons and hadrons. Hadrons are all made out of quarks, which are held together by gluons. 8 of them, 6 leptons. I've left for the moment open the question of how many quarks are there. Now, in 1964, when Gell-Mann first published this theory, he proposed that there were 3 quarks, to which he gave the names up, down, and strange. We only need up and down quarks together with electrons to account for all ordinary physics and chemistry. Those particles, those 3 particles, up and down quarks in the appropriate combinations, will give you protons and neutrons. The electron, of course, would then combine with the protons and neutrons in order to make all the atoms that we're familiar with. And the laws associated with protons, neutrons, and electrons, as, for example, in quantum electrodynamics, would allow us to account for all of the ordinary physics and chemistry. When you get to higher energy levels, for example, if you want to understand what goes on in the interiors of stars, how stars work, and you remember that Hans Bethe's 1938 theory began to give us an understanding of the fusion processes that go on inside stars. If you want to understand what's going on in the upper atmosphere when cosmic rays collide with the upper atmosphere, then you're going to need to use the quark theory much more intensively. Then you're going to have to involve the strange quark. Let me step back for a moment and make a comment about these names, which clearly are whimsical. That is to say, calling the eightfold way, the classification scheme, the eightfold way. All right, that's kind of cute. Calling the particle omega, that's kind of cute. But then calling particles quarks, calling the quarks up, down, strange, and there are 3 more to come, charm, top, and bottom. Calling the particles that hold them together gluons, and giving them color, saying that they carry a color charge. And then Gell-Mann gave the name, he's responsible for all of these names, he gave the name quantum chromodynamics, chromo meaning color, quantum color dynamics to the whole theory of the strong force. That's what it's known as, QCD, quantum chromodynamics. That's explicitly whimsical. Now, why is that? Are physicists making a joke out of this? Now, as a matter of fact, there's a very important and serious point here. Earlier quantum theory, especially between 1912, Bohr's quantum theory of the atom, and the 1920s, continued to use 19th century physics names for quantum level phenomena. One of them being, for example, the spin of the electron, that particles have a spin. Now, they don't really spin. Classical particles spin, and we understand what spinning means, but when you use these names at the quantum level, that generated all kinds of conceptual problems that physicists had to escape from in the 1920s and 30s. The quantum level is, remember what Bohr said in 1929 about complementarity, and the quantum level is beyond our experience. When we assign names from our experience that have connotations from our experience to the quantum level, we are guaranteed to create conceptual problems that we have to say, well, it's called spin, but it doesn't really spin. None of the things associated with spin, like the angular momentum associated with spinning, for example, don't worry about any of that. It's much better to give these whimsical names that have no connotations in physics. The fact that somebody thinks, that's pretty funny, calling a particle charm or top. Couldn't you think of a better name than that? So in 1964, this theory, quantum chromodynamics, begins to give us a radically new theory of matter, a quantum theory of matter. Now, quarks are really peculiar particles. Quarks have mass, they have spin, we're stuck with that, and they have fractional charge. They don't come in whole electric charges like electrons. They have fractional electric charges, which is why you have to have multiple quarks in order to get an electrically neutral proton or neutron. In order to put it together, you've got to have the right balance of quarks and antiquarks with charge and negative in order to get whole charges. Quarks and antiquarks, unlike matter and antimatter, combine constructively, not destructively. They're very happy together, quarks and antiquarks, so to speak. Quarks are much, much smaller and much, much lighter than protons and neutrons, or any other hadron that is made up out of quarks. Well, the much smaller part we can live with, because we know that the nucleus is much smaller than the total volume of the atom. And then we learned in the 1930s that the protons and neutrons are actually much smaller than the nucleus. So the fact that quarks are much smaller than protons and neutrons doesn't scare us, but they're much lighter. So where does the mass come from? You recall that in the early 1930s, a major question that physicists confronted was, what are we going to do about the fact that atoms weigh more than the electrons and protons that they're made of, something that they had known since the 19-teens, and they sort of had vaguely said there must be some neutral, electrically neutral stuff in there that gives it the extra weight. In the 1930s, that stuff became the particle called the neutron. Here, the explanation is very different. Here, the explanation is that quarks move so rapidly that through the relativistic effects, they acquire the proton particles like protons made up out of combinations of quarks seem to have more mass than they, in a certain sense, actually do. That the bits and pieces, the quarks, that are the constituents of the proton weigh, if you could quiet them down and put them on a scale, they would weigh much less than the proton. But because they're not quieted down, they're whirling around and they're moving so rapidly that relativity theory needs to be applied to them, that's where the mass comes from. This turns out to be very relevant as we move into unification theory, and we begin to recognize that we should uncouple in our minds the concept of mass from solidity, because mass can be quite deceptive. So we have now, in 1964, 3 quarks, 8 gluons in 3 colors, 6 leptons. And we can, in principle, build particles out. We can build all ordinary physics and chemistry out of this. But in fact, we can't account for everything that there is to be accounted for from just these 3 quarks. And we are going to telegraph it, we're going to have to acquire 3 more quarks. In 1973, at the Stanford Linear Accelerator, in a team led by a physicist named Burton Richter, independently and at almost the same time at Brookhaven National Laboratory at their particle accelerator, and a team led by Samuel Ting, discovered a 4th quark, which was given the name CHARM. That was in 1973. In 1977, at Fermilab, Leon Lederman discovered a 5th quark. Lederman discovered a 5th quark, which was given the name bottom. I don't think this had anything to do with Shakespeare's Midsummer Night's Dream. It was in anticipation that there might be a top quark around somewhere. I happened to be visiting Fermilab at that time, and coincidentally was present when Lederman got a telegram from the particle accelerator team in Hamburg, Germany, confirming his discovery of the bottom quark. That is to say, they had confirmed the experiment he did at Fermilab with his team, whose results he interpreted as a new quark. They were able to replicate that resonance and get that same result. And I remember asking him, well, do you think quarks are real? Back in 1977, you could ask this question. And I said, do you think quarks are real, or is this another intellectual construct? And he said, well, you know, when Gelman said there were 3, I thought they were real. 4, that was okay also. If I'm right and there are 5, then there have to be 6. 6 are too many. So there must be something more fundamental than quarks. I don't think he has that opinion today, but that was his off-the-cuff response at the time. So the bottom quark was discovered in 1977. It took another 18 years and major upgrades to the particle accelerators at Fermilab and CERN by 1995, when the top quark was discovered. the energy level of the Fermilab accelerator had reached 1.8 trillion electron volts. And finally, after 12 years of trying, the Fermilab team found the top quark. They had to examine 16 million collision events in order to identify a literal handful of candidates for the top quark. 16 million collision events. In fact, while they announced the discovery in 1995, the data had actually been taken several years earlier. It took several years in order to process the data that had been collected during the 1993 run at the accelerator in order to find out that they had, in fact, observed the top quark. And as I mentioned at the close of the last lecture, the size of the team that discovered the top quark is all by itself quite interesting and revealing about something about the evolution of science in the 20th century. You know, we have this sort of romantic image, especially from the late 19th and early 20th century, of the lone genius. You have this figure of, you have an Einstein working here, you have a Bohr working there, you have an Ernst Rutherford working here. And yeah, we vaguely know that in some cases, not Einstein's, that they had graduate students, that they had a lab team, etc. But we tend to, it's part of, I think, of a cultural prejudice of ours, we tend to focus on individual heroism. And we think of the individual genius who makes these intellectual or cultural or artistic breakthroughs, a Picasso, an Einstein, etc. But the team that discovered the top quark was 440 strong. The paper had 440 co-authors on it from 35 different institutions in over a dozen different countries. Physics, by the end of the 20th century, had become highly collaborative. And there were not just physicists involved here. There were physicists, there were mathematicians, and there were computer scientists and engineers who were associated with building the detectors, with processing the information, and the announcement of the top quark was sort of completed quantum chromodynamics. This was in top quark 1995, but the fact is, between the formulation of the strong force theory, quantum chromodynamics, in 1964 to the end of the century, the strong force has so far resisted all of the challenges that have been mounted against it. It doesn't mean that there are no problems. There are certainly problems that the strong force has not been able to resolve fully. One of them has to do with the fact that neutrinos, when Gell-Mann formulated Gell-Mann and Zweig first formulated the quantum chromodynamics, before it even had that name, back in '64, they thought the neutrino had zero mass. In the mid-'60s, observations of neutrinos coming from the sun suggested that neutrinos, in fact, had some mass. This was initially highly controversial. Things went back and forth for a dozen years or so, but at the close of the 20th century, it is generally agreed that neutrinos have some small amount of mass. And so far, quantum chromodynamics is not able to explain that phenomenon, to account for even the very, very small mass that neutrinos are assigned. So that is certainly a problem. There are other problems having to do with the energy of protons, but by and large, the quantum chromodynamics, the theory of the strong force, by the year 2000, was pretty firmly in place. And we now had a platform on which to attempt unification. Now, that makes sense logically. As a matter of fact, as we will see as we move into the next lecture, the attempt to start unifying the forces of nature actually begins in 1961, and even earlier than that, but the successful attempt begins in the 1960s, just in parallel with the formulation of the theory of the strong force, to start uniting the forces of nature. And the first pair of forces that we attempt to unite will be to unite the electromagnetic force and the weak force. And why that should have been the first choice will be the starting point for our next lecture.